just waiting for the clock to turn to 12. All right, so the last time, where did we stop? Do you remember? Where did we stop last time? We're talking about the definition of temperature.
The Carnot cycle?
Yeah. And at the end of the class, we give the definition, right? We combine the first law and the second law of thermodynamics, and eventually we get this relationship, right? EU equals to what? TdS minus PdV, right? And here's something very important we need to keep in mind. One thing is that this equation only work for the gas, okay? Yeah. This equation works for gas, okay? Because we only talk about pressure and volume. We do not talk about something else. Magnetic orders and potential energy, we do not mention them, okay? So we only consider the pressure and volume. That means this is the gas system. And the other thing that since we use the equal sign here, that means we are describing the reversible process, okay? Only for the reversible process we can write the equation in such a way. Otherwise, we need to make some modification to it, okay? But anyway, so again, another thing is important. We write this equation in form of the derivative, right? That means only this equation describes a very tiny process, not the entire process. If you want to calculate the entire process, we need to do the integration on both ends, okay? From that one, you can see the temperature shows up, right? So then we can give a definition of the temperature, or we can calculate the temperature in this way, right? If the gas have the one constant volume, the temperature is defined. It can be calculated as the function of the internal energy, the variation of the internal energy as a function of entropy, right? Any question here? This is pretty straightforward, right? So we just find another way to calculate the temperature instead of measuring it. Actually, you can calculate nothing because we have not mentioned about how to calculate or how to measure the entropy here. So basically, but we know that the mathematical expression of it. Then here comes an interesting problem. I asked you to check the YouTube to talk about the negative temperature. Have you done that? Anyone of you check the negative temperature? Or no? No one check negative temperature? Okay, anyway. I cannot show the YouTube video in my classroom for sure. Okay? For two reasons. One reason is I'm mastering in the classroom. I'm the only one who authorized to give the talk. The other thing that YouTube has copyrights. I don't want to go back to my office and the lawyer's letter on it. Anyway, so but look at this equation. So what that means if we have a positive temperature. Positive temperature means what? Means as the entropy, now the internal energy of the system increases, the entropy also what? Increase, right? That what I'm saying? So what is the positive temperature mean? For example, this is entropy, this is the internal energy. What does the positive temperature mean? Mr. Derivative, right? Let me check it out. So the curve should look like this, or the curve should look like this. Which one gives us the positive temperature? This one, right? Because temperature basically is just a slope, right? This one has a positive slope, right? So we know that if we have a high temperature, then as the entropy goes up, the energy goes up, correct? This is the normal behavior according to our normal understanding. Okay, so right now consider one interesting case. Still remember I told you something when we talk about distribution and thermodynamics at the beginning of class. I mentioned a mobile, the parking garage. Remember? The parking garage is the first floor, this is the second floor. Okay? First floor and second floor. So, your car, which floor gives your car a higher energy? The second floor, right? If your car located on the second floor, you will have the higher energy, correct? But in the random case, as I mentioned last time, So it's unlikely for everybody just to find exactly the position you want to go. Sometimes you cannot find the parking spot, although it's probably hidden somewhere else, but you cannot find it. So what do? You just go to second floor, right? So that means your distribution is most likely something like this, right? You have more cars on the first floor and second floor, correct? This is our observation, correct? Have you ever seen any kind of parking garage have more cars on the second floor than the first one? It happens, it happens. For example, the first floor all reserved for faculty. Then all your cars go to second floor, right? Or you have some gaming day or whatever. How do you think about the game day? Is that disturbing your parking? How many of you came to campus last weekend to watch the game? Is that good? Is that easy for you to find parking garage, parking spot?
I didn't drive.
Huh?
Just Uber, get a ride. It's not worth it.
Yeah, I know.
It's too much work.
But anyway, so think about it. First of all, let us put all the cars on the first floor. Put all the cars on the first floor. Let's make them have the order. Everything is ordered, okay? So as you know, I think most of you already know, the entropy means the order of the system, right? So if every car is located on the first floor, what is the energy?
Zero.
The energy can be 0, right? What about entropy? If everything is in a good order, we know that the entropy is very low, right? We can define it as 0, although it's probably not 0, but let's find it 0. Okay, right now, I give energy to a system. Allow one car to move from first floor to the second floor. Then the energy goes up, right? The energy goes up, correct? Energy plus 1. Correct, everybody? What about entropy? It's become more disordered, right? And that means the entropy also goes up, correct? Right now, if I move two cars on the second floor, energy increases or decreases? Increases, right? What about entropy? Entropy also increases, right? So the temperature of the system is what? Is positive, right? Okay, let us consider the extreme case. So today is the gaming day. And the UCF police officer came. He told you cannot park on the first floor, otherwise you have a citation. Okay? Then what will happen? But the second floor is not reserved, right? So then all the cars go to the second floor, right? And the first floor is empty. Okay? Think about the case. You only have one car or two cars here, right? Then the UCF police came, right? Okay. Right? So what will happen for this car? It just rushed to the second floor, right? What about energy? How does energy change? Huh? Increase, right? Because we are keeping pumping the car to the second floor, right? What about the order of the system? Or entropy? Entropy going up or going down? Entropy going down, right? Because, I mean, eventually, at the beginning, we have some car on the second floor, some car on the first floor. It's very messy, the system, right? But right now, everything has really good order on the second floor. That means it's from one disorder state to another order state. Although between them, we have some disorder state, correct? But the final state have high energy, right? Think about it. If we move the last car from first floor to the second floor, the energy still goes up, but entropy going down, correct? Then what's the temperature of the system right now? It's positive or negative? You got confused, right? Look at the system. The energy goes up, but entropy going down. What's the temperature of the system right now? Huh? It's positive or negative? Seriously? Partial U, partial S. S goes up, U going up, S going down. U goes up, S going down. It's something like this. What about slope here? What is slope here? It's negative, right? temperature in this case is negative, okay? I mean, it's very anti-intuitive, but it's indeed negative. So, for this kind of system, we give a special name. We call it two-level system. Okay, if you have 3 levels, it's more complicated, but this is we call two-level system. For the two-level system, sometimes it exhibit some very interesting behavior. So we have the U here, we have the S here. Okay, at the beginning, when the no, running that way, it's U, this S. At the beginning, the S increase and the U increase, something like this, right? But eventually, as we reach the maximum value, okay, and then further as the U further increases, the S decrease. Okay. But you know this kind of plot is not a function anymore, right? Because for each of the value of S, we have 2 possible values of U, right? So eventually you'll find that T actually is not a very good definition to describe the thermodynamic process. Instead, sometimes we use 1 over T. Okay, 1 over T. So how do we find the value of 1 over T? So it's simple. So we just make some modification to this equation. We know that du equals to Tds minus PdV. Correct, everybody? We just move something like this. So we have Tds equals what? Minus du plus PdV. Is that right, everybody? Correct? And then we move the something like this. Right? Correct? Then what we have is 1 over T equals to what? I made some mistake. We don't have my sign. Equals to what? Equals to partial S, partial U, and a constant B. Okay. So this definition allows us to flip this chart. Okay, we can use the U as independent variable and S as dependent variable. Okay, so that means as the U increase, the entropy going to increase and eventually going down. Okay, and 1 over T and 1 over T as a function of U. 1 over T. Basically 1 over T means the slope of this curve, right? Correct, everybody? It's positive, going down, something like this. This is just first order derivative of this curve, correct? And this is 0 point in this point, right? That's the maximum point, right? You can see that the 1 over T goes up, going down, go to 0, and become negative, right? But of course, if you want to plot T as a function of U, if you plot T as a function of U, then the behavior looks really weird, right? Because you need to flip it, right? Then it becomes something like this. Go to infinity large, and suddenly drop to negative, right? Correct? Because you have the 0 point. 0 point is not well defined. It can be positive infinity or negative infinity. Right? And at this point, have some like phase transition point, right? The temperature is positive and suddenly become negative, right? Other point? I mean, it looks very unusual, very unnatural, but if you plot 1 over T, it looks more normal, okay? Then we have a very interesting conclusion is negative temperature. If the system has negative temperature, somewhere here, it typically have higher energy than the system with positive temperature, right? That means the negative temperature system is more energetic than the positive temperature system. Understand what I'm saying? So that means if you can find a system have a negative temperature, it should be hotter than the system with the positive temperature. and energy flow from negative temperature to the positive temperature. Correct, everybody? Hmm? And something? Hmm. Then let's go back to explain why laser can cut. Why laser can cut. For the laser system, the same thing. So the, do you know what is LED? The light emitting diode, right? The LED beam is from the semiconductor material. Exactly the same thing. We have two energy levels. Okay, it's not parking garage, it's energy level. So we have electrons on the second floor. We figure out a way how to put all the electrons on the second floor. Okay, and on the first floor is fully empty. Okay, we managed to do that, but you have different way to do that. But that's not the point. That's not the key point. The key point is if we reach this state. Of course, the electron want to prefer to go to the ground state or bottom level, right? But right now, every electron is on the higher level. Then the entropy is what? Is negative. The entropy is low, right? Because every electron on the second floor is have really good order, but the energy very high. Correct? So for this kind of system, the temperature is what? It's negative, right? It's negative. Okay? And we give it a special name. We call it the population reverse. Inverse, yeah, population inverse. Population inversion. That means we have more population on the high energy level than the lower energy level. Okay, that's the population inversion. And this system has a negative temperature. A negative temperature. But which one is hotter? Negative temperature are hotter or positive temperature is hotter? Which one is hotter? Negative is hotter, okay? Then that's the reason if you have a laser pointer, even you have a laser pointer, that's no problem. If you have a laser, you focus the beam onto the stainless steel, you can cut it, right? Because it's very hot. The negative temperature system is very hot, so it can melt the metal. That's the reason why we can use a laser to cut. Other points? Huh?
I just have a question. The negative temperature thing is strictly like a naming convention that's derived from the like when you graph out the function, really high temperatures come out as a negative, like kind of a asymptote or something. Is there any practical reason why they continue to call this like a negative temperature? I mean, is there any like real world? I don't know. I'm looking for like a very tangible, hands-on reason why this would be a negative temperature versus just, hey, it graphs out weird, we call it negative because of that.
No. Okay. I mean, the reason is people find the negative temperature only because we find another definition of temperature. Okay. Partial U, partial S. And we call it the negative temperature just because of that. Okay. That's the reason why I call it this kind of definition very anti-intuitive. Okay. Okay. But keep in mind, negative temperature is hotter than positive temperature. Okay. And the other thing you should also keep in mind, if you warm something, you want to warm up something with a thermodynamic way. You either warm it up, or use the cook, or use whatever to bring the heat into the system, warm it up. You can never reach the negative temperature. Okay, negative temperature is reached. It cannot be reached through a thermodynamic way. Okay. So for example, this kind of laser diode, we do not warm it up. Right? Think about the, we do not use this kind of light anymore. You know that we have the tungsten coil inside the light and use the electricity to warm it up, start glowing. That is a thermodynamic lamp. Okay, it's a bay, this kind of something like have positive temperature. But you know the laser diode, we don't do it that way, right? We have to put the semiconductor material inside and use a battery to do the job, right? But that's again, so battery can drive the laser diode. Right? That means the battery can put energy into the laser diode, right, everybody? So what's the temperature of the battery? What's the temperature of a battery? Right? The battery should have negative temperature, right? Because the energy can only flow from the high temperature to the low temperature, right? Naturally, spontaneously, right? So if the laser diode have the negative temperature, then the battery should have what? The negative temperature, right? It cannot be positive. If it's positive, then the energy flow in the other way.
So it's just a term for energy?
Huh?
Is it completely dependent on like terms for energy?
It depends on energy and also depends on the order of the system. Even the system has really high energy, but this has a lot of disorder, then the temperature can still be positive.
So it completely depends on the material's property, right?
I mean, let me change it the other way to
Because
explain that.
physical heating cannot change the material to, reach negative.
No?
Physical heating of material, let's say.
Yeah.
It will not help, or it will never let a material to achieve the negative temperature, right?
You can. You can make a material to achieve negative temperature.
By physical heating?
No.
Yeah, that's what
By
I'm
physical heating, no. You cannot.
So it depends on the material's specific property, right?
Yeah. It depends on material specific property. As long as you know you use the heat transfer or whatever, you can never reach the negative temperature. You have to find another way to do the job. You know what I'm saying? Either use a battery, use a laser, use whatever. Okay?
So what's the nature of energy we need to?
The energy is energy. There's nothing about it. Energy is very, think about it. As I mentioned at our class. So energy is one driving force for the system to spontaneously reach the equilibrium states. But we're talking about state-specific system, right? What about the other one? What's the other factor decide the direction of the system, of the evolution of the system? The entropy or the possibility is going to become more and more disordered, right? The system has high energy. The energy wants to go to the lower energy, yes, of course. But the other thing is whether the system is disordered or not disordered. The system is themselves always want to go to disordered state, right? So think about this system. This system is highly ordered, right? These people want to become disordered, right? If it want to become disordered, it's also bring the energy to the subsystem, right? It become disordered, then the electron jump up. It's release energy, okay? So in that case, the negative temperature, the driving force, not only the energy but also the order. Okay, we have to consider both factors. Okay, but think about thermodynamics. Thermodynamics is more like the temperature driven. Okay, but for that one, it's more complicated. Okay, but for here, I only explain you what is the negative temperature. But right now, keep in mind, the negative temperature is hotter than the positive temperature. So, from the next class, I'm going to talk about the statistic explanation of the entropy. So you'll have a better idea about how this happens. Okay? And what is your question?
Yeah, so like the third law says absolute zero can never be reached at that particular point. But if like in this two-level system, if I have two electrons on top, two electrons in the bottom, the
Yeah, you're right.
is zero.
One thing is like this. So you're right. I mean, the absolute zero temperature cannot reach, right? But we are not reaching the absolute zero temperature is here, right? We reach the negative not through this point. I mean, we are not reaching negative from this way. You know what I'm saying? Not through the 0 point.
Oh,
but we
so-
through the positive infinity and immediately jump back to the negative infinity.
Oh, so at that point, it's not t equals zero. It's
No.
actually t is infinity.
Yeah,
Oh.
exactly. So you can see that think about it. If 1 over t, what's the function looks like? The function can looks like something like this, right? Right? It can go to negative 3 point, but it can also go through a negative from infinity, right? So we reach the negative from this direction, not through this direction.
So if I have two electrons on top and two on the bottom, the temperature is infinite.
You can say that, yeah, that's true. Yes, you can say that, but 2 electrons is not the statistic system anymore. Okay. But strictly speaking, if all the electrons just on the top, yes, it is infinity. Okay, but it can be neither positive or negative because we do not know which one I'm talking about. Right? So, for example, if the electron jump down, then the energy going down, entropy going down, this is positive. And if this is reached by remove this electron from bottom to top, then the energy going down, entropy going down is negative. Is negative, right? So in that case, you can see that infinity large roughly equals to minus infinity. Roughly the same. Okay,
So-
we are talking about the same thing. It's just about whether you do the derivative on this one or on this one. But mathematically speaking, there's no definition because the equation is not continued on this point. Right? So we have no definition of the total derivative, mathematically speaking, on this very specific point. Right?
So is it like let's say there's a disorderedness and once it reaches 50%, let's say,
Yeah.
and then it changes its nature
Uh,
from positive to negative, right?
uh,
So it completely depends on the disorderness.
yeah. It's
So
depend on
once it
this
reach, like, once it crosses 50%,
Mhm. It's not here.
relative.
No, it's not the 50%. I mean, if you want to say 50%, it's something here. Okay, 50% is something here.
Yeah, exactly.
Yeah,
That's what I'm saying.
It's something there, yeah. And this one is roughly 100%.
Yeah, so then
Yeah.
it changes its nature,
Yeah,
right?
it changes, suddenly change. Okay, that's the reason we call this one is something phase transition. Okay, it's a phase transition on this point. What's your question? You have some question?
Me?
Uh,
Oh, it's not what it would, it's not, you drew a tangent, but it would never cross zero, just keep going.
yeah, it doesn't go across zero. It goes to this direction. Goes to infinity and suddenly jump to the bottom.
Yeah, never mind.
And it's always relative, right?
Huh?
It's relative to the previous.
It's not relative. We can calculate precisely to see whether it's not relative temperature. It's absolute temperature. Okay. But you come to one question. We can calculate the internal energy, but how can we calculate the entropy? So far, we have not given any kind of answer about how to calculate the entropy yet, right? So this is the job for the next chapter. Okay. But let's go back. Let's go back. Continue your question. Entropy. Okay. Now think about one thing. Since I already tell you how the system can reach the negative temperature, then ask your question, why the battery, a simple battery, with any kind of battery, is at a negative temperature? What's the reason for that? What is that garage parking model corresponding to the battery system? Think about it. Okay? But anyway, so again, let's go back to entropy. It's very mysterious, right? So we know from our discussion, we know for a reversible process, this one is defined, this one is expressed as that one, right? For a reversible process, right? Is QT. And this one is a little bit misleading. It just gives us opinion or idea or impression that the entropy is related to the heat exchange. Correct, everybody? So because I want to make some emphasis or clarification. Okay. So first, this is not a definition. Okay, this is not a definition of entropy. Okay. Okay? Instead, it is only a way to calculate S for a reversible process if delta Q is known. Okay, this is very important. This is not the definition of entropy. Okay, it's only tell us how can we calculate the entropy if for a reversible process and if the delta Q is known. Okay, we can calculate, but this is not definition. So what's the definition of entropy, by the way? So again, this question will be answered in the next chapter. But I can tell you, the entropy is defined in such a way: it's K, the Boltzmann constant, ln, and then we call it omega whatever. So omega is the number of the microscopic state corresponding to the equilibrium state. Okay. That means during a thermal equilibrium state, how many different kind of a microscopic configuration the system can possibly have. Okay, this is the definition of entropy. Okay, but it's so complicated. So we typically do not use it. Okay, instead we can use this kind of expression to calculate in an easier way. Okay, but again, that's not the definition. Okay, everybody read after me. This is not the definition of entropy. Okay. That's one thing you want to be very careful. Okay. The other thing is, I already mentioned, this is only for the reversible process. But if the process is irreversible, then we have this one, right? For irreversible. Okay, process. Process. Keep in mind. The other very important thing I want to keep in mind, okay? The other very important thing I want to keep in mind. S, I also emphasize several times, okay? S is a thermal dynamic parameter. Wow, we can always write it down. Thermodynamic parameter. Similar to P, V, U, T, whatever, okay? You name it. Entropy, although you can calculate through the heat, but it's not heat, okay? It's a state parameter or thermodynamic parameter. What does thermodynamic parameter mean? Can anybody remind me what the thermodynamic parameter mean?
It only matters the beginning and end. The process doesn't matter.
Exactly. Okay. It's only defined by the state. Okay. For example, let's still go back to the PV chart. Okay. The gas. So we have the A state. We have B state. Okay. If we already know the state A with a function of PV, theoretically speaking, we can calculate the SA. Okay? And the same thing here. This one is all defined by the state of B. Okay? You know what I'm saying? Or let me write it in bad way. So the SA is only a function of the PA and the VA. Okay, the same to the SB. Okay, PB and VB. Okay, it's independent of the loop connecting these 2 points. Okay. Okay, and then the change of the entropy is what SB minus SA. It's independent of the specific loop or path that link A point and the B point. Okay? You can link the A point to the B point, for example, with this kind of the path. You compress the gas or expand the gas, whatever. You can also link from the other path. Okay? Give the same result. And even the path cannot be drawn on the surface, on the whiteboard. So what that means? This is an irreversible process. Okay? Even you link A and the B point through the irreversible process, the change of the entropy is still the same. Okay? Got my points? And this gives us one way to calculate the entropy, even we do not know the details of the thermodynamic process. Correct? Even we do not know the details. As long as we know the first state and the final state, we can calculate it. Right? Correct, everybody? And in another word, even we do not know the specific path, we can always artificially, even we do not know the specific path, we can artificially find a loop or find a path to link these 2 points and use that equation to calculate the change of the entropy. Everybody agree with me? Got the point? Any questions? If you have no question, let's do one practice. practice. C or S? What about S? Huh? Practice. Okay? 1. Calculate the entropy change during free expansion, not free expansion. Adiabatic. Hold on, let me see whether we need to mention this adiabatic or not. Yeah. Is that clear to everybody? You can see that letter? I did not erase the background properly, but I hope that you can see what I'm writing here. Calculate the entropy change during the adiabatic free expansion process in which 1 mole of the ideal gas expands from the A to B. Okay? So if you write on chart, this is the V, this is the P, this is the A point, this is the B point. Okay? And for your reference, so free expansion means something like this. So we have a tank. It's thermal isolated from the environment. So what? What's the adiabatic mean? Delta Q is 0, right? We'll see the adiabatic. You will know that delta Q is 0. Okay, that means this container is thermally isolated from the environment. Okay. Then we have the gas, first of all, confined probably in the lower half of the container, and then it suddenly expands to occupy the entire container. Okay. This process we call it free expansion. Okay. So anyway, so I give you about 10 minutes for you to do the calculation. Okay. First of all, we know that. Do you think this is a reversible process or irreversible, right? Process.
Reversible?
Huh?
Reversible?
Reversible? Okay.
No, irreversible.
Irreversible. I mean, you have the tank, you have gas confined in the bottom, and suddenly release it. Do you think the gas will spontaneously got confined in one corner of the container anymore?
Can be possible with work.
Huh?
It can be possible by providing work, right?
Yeah, of course, that you improve the work, but I'm talking about spontaneous.
Okay, okay. Yeah, right.
Yeah. If it cannot spontaneous go back to the original state, it's irreversible process. Okay. Anyway, do the calculation to see how it works. Yeah.
Yeah, I have a question. If
Yeah.
you could draw a curve connecting A to B,
Yeah.
and A and B has different entropy, doesn't that mean like you can spontaneously go from like B to A as well?
Yeah.
Or-
You
because
can
it's-
spontaneously go from A to B.
but
No,
if it's
no.
reversible, doesn't it mean it's spontaneous?
No. Reversible and spontaneous are different things. Okay. I mean, the reversible, that means the reversible process not necessarily means the entropy doesn't change. Okay. But fitting to this question, I will explain to you. Okay. Spontaneous process means the entropy always increase. Okay, that's a spontaneous. And the reversible process means it's not. Reversible process. Reversible process is not related to whether the data has changed or not. You know what I'm saying? It can go up, it can go down, but I will explain that to you later. Actually, reversible process is something like this. So there you can draw. If you can draw a path on this chart, it means it's reversible process. Okay? But for irreversible process, you simply cannot draw the line. You cannot find a path to link A and B point. Done?
I'm not sure.
Do you guys actually know how to do this?
Huh?
I was asking the class if they actually know how to do this. I don't. I feel like I look back at my notes, I think I know the answers, but I have no idea.
The reason is that's true.
Then
But you need to do the integration. The integration is the function. You need to do the integration.
This is the first demo class that I took. What's your I must have missed it. I should have found it.
But roughly the right direction. The direction is right. But you need to do the integration. If I give this question to ChatGPT, do you think how soon can you solve it?
Already done.
So if you cannot solve it, why I need to hire you? Oh, by the way, so I have no idea whether I need to talk about it. I give you a question, okay? A geometry. Not geometry, it's the geometry. Geometry? Or geology or geometry question, okay? It's some high middle school student give me this kind of question to me. During the weekend, I dropped that question to the AI. It solved that probably in 1 minute. I spent about 2 hours to solve it. Okay. Anyway, let's finish that one first and talk about that question. And I will draw on this whiteboard, so it won't be broadcast. Okay. Unless students, you will not see this question. Okay. It's not related to thermodynamics. Only in class, students will see that. Anyway, so have you figured out how to do this job? Okay. Again, this is the irreversible process. Correct, everybody? So we have no way to link, we have no way to find a path to represent this kind of irreversible process on this chart. Correct, everybody? But let me go back to the, let's analyze the process. As I mentioned, if you want to calculate the change of entropy, it's not necessary for you to know the specific path, right? You can find any kind of artificial path to link these 2 points and calculate the entropy change. Correct, everybody? So any path, whether it's reversible or irreversible, all of them should give you exactly the same delta S, right? This is the definition of thermodynamic parameter. Okay, so adiabatic means delta Q equals 0, right? Free expansion. We already mentioned for the free expansion, how much work done by the gas to the externals? 0, right? Then we know that the delta W equals 0, correct? So think about it. Du equals what? Delta Q minus delta. Correct, everybody? Then what about this term? 0, right? Correct, everybody? Then, exactly. It's just like the isothermal process, right? The isothermal process means that the T doesn't change, right? But for this case, it doesn't change. Right? Think about it. The only difference is delta Q equals 0, delta W equals 0. But for the isothermal process, delta Q equals to delta W, but the same thing, delta equals 0, right? So in that case, we can link this 2 state with the isothermal process. Correct, everybody? So in that case, we don't even talk about whether it's adiabatic, free expansion, whatever. But we know these 2 points can be linked through the isothermal process, in which the temperature is constant. Because at the final state and initial state, the temperature doesn't change. Correct?
How do
So-
you know that the temperature doesn't change?
Because it's a free expansion, we do not do work. And then there's the adiabatic, there's no delta Q. Then the total delta U equals 0, right? The U doesn't change, internal doesn't change, the temperature of the ideal gas doesn't change. Anyway, so we know that one. So then the job is relatively easy. So for the isothermal process, the key point is we can use isothermal process to build this path in order to calculate delta S. Okay? And the delta S is independent of the specific path. Then the delta S also, and then for this adiabatic free expansion also should give us the same delta S. Okay? So then we can calculate the delta S from the, we can calculate delta S equivalently equivalently, I spelled it wrong. Anyway, you know that is equivalently, okay, from an isothermal process. Okay. For the isothermal process, we know that the delta Q equals to delta W equals to PdV. Correct, everybody? Then, the delta ds equals to delta Q divided by T equals to P divided by T times dV. Okay, because we already mentioned it's 1 molar of gas. Then the PV equals to RT. Correct, everybody? The PV equals to RT. We put it here. Then you have what? You have the R divided by V dV. Correct, everybody? right? P divided by T equals to R divided by V, right? And then we do the integration from A point to B point, ds equals to VA to VB, R, V, V. And then we have delta S equals to R times ln VB divided by VA. Okay, that's the result. Okay, that's a change of the entropy. Although we don't know the specific details, but we still can calculate the entropy change. Got the point? All right. So, answer your question. I mean, finish your job. Finish the job. Everybody done? So then we have some discussion, okay? Answer your question. So what is reversible process and what is the difference between reversible and irreversible process and spontaneous process? Okay? Look at it. We know for this adiabatic process, the delta Q equals 0, right? The delta Q for the adiabatic process equals to 0, right? But the delta S is something like that, right? Is R times ln VB minus V divided by VA. That's the change of the entropy, right? And the delta Q through the entire process equals what? Equals 0, right? And you will find that delta S actually larger than delta Q divided by T. Correct? This is the irreversible process. Correct? And for the isothermal process, we calculate from this equation, then the delta S equals to delta Q divided by T. Correct? So that's the difference. So we distinguish reversible and irreversible process by judging whether this equal sign stand or hold, or we use that one larger than something. You know what I'm saying? It depends on the relation between the change of entropy and the heat. This can be served as a criteria for us to distinguish the reversible and irreversible process. Okay? And on the other hand, more practical way, as long as you can draw a curve on the PV chart, is a reversible process. But if you cannot, it's irreversible process. Okay? Got that point? And the other thing, probably you got confused. So what about spontaneous? Spontaneous process only means delta S larger than 0. If the delta S larger than 0, then it's a spontaneous process. Look at about these two processes, okay? Let's go back to talk about these two processes. We have two processes, right? Link A point and B point. Okay? We have two processes. One is isothermal process. The other is the free expansion process. The free expansion process happens spontaneously. Everybody agree with me? So as long as you set this atom for free, they just spontaneously go to the other half of the container. Correct, everybody? This is a spontaneous process. Isothermal process. We have a container, we have compressed gas inside. Right? And then if you remove your hand, do you think the piston move above? If the gas inside is pressurized, do you think this piston can go up spontaneously? It also goes spontaneously, right? Because that's the reason both cases, isothermal process and free expansion process, all has delta S larger than 0, right? But one case, delta S equals to the Q divided by T. That is the isothermal process. And on the other hand, the other process, delta S larger than delta Q divided by T. That's a free expansion process. Okay? Got my points? So this is how we What's the difference between spontaneous and inspontaneous, and reversible and irreversible process? Did I myself understood?
Yeah, but like you could still say that you firstly go from A to B through that dashed line where
Yeah.
you cannot draw
Yeah.
the process, and then you go back from B to A with the isotherm line, and like
Let me tell you.
I'm still saying it's reversed.
You are talking about the loop. You are talking about the loop. You are talking about the loop. Yes, for the loop, it's a different story. Okay, it's different. It's a little bit different. Okay. Then this spontaneous and reversible and irreversible start to have some overlap. Let me show you. So this is P, this is V. And you mentioned we have A point, we have B point. We can link this one from isothermal process. Because this one is the iso process, and then this one is a free expansion. Correct, everybody? Free expansion, right? So you can see that we can from A to B. For example, from A to B, we use the isothermal process. From A to B, we can make them to have the free expansion. Correct? And then we can go back from B to A. We use the isothermal process. Okay? That means we form a loop. We start forming a loop. Okay? Then we have this loop. Correct, everybody? We have this loop. Then we know that. Then we have the delta S from A to B plus delta S from B to A. That means that equals to what? Huh? 0. Right? This is 0. Correct, everybody? This is always 0 because we only consider, right now we only consider this tank. Okay, we only consider this tank. So in that case, we have something like this. Right? Because it's go back to origin point. Correct, everybody? It's go back to origin point. So there's no way for you to tell whether this kind of the process happened like spontaneous or reversible or irreversible. Correct, everybody? And if we need to analyze, we need to consider some other factors. If you already consider the loop, we need to consider the environment because you start to exchange the heat from the environment. Correct, everybody? You start to exchange the heat from the external, right? Right now, let's consider in that case. Let us consider you put this tank in an environment, okay? In an environment, you have the reservoir of heat. In reservoir of heat, right? We know that for the free expansion, there's no heat exchange. Correct, everybody? For the free expansion, there's no heat exchange. Then the entropy of the external doesn't change. Correct, everybody? And for that one, for this kind of isothermal process, right now it's not expansion, it's compression, right? Because we go to the other direction. Then it's release the heat to the environment. Correct? Right, everybody? Right? And then what's the entropy change in the environment? Is equals to delta Q divided by T. Right? And this one only works for the, this expression only works for the cylinder. And if you want to consider the entire system, you also need to add the environmental part. Okay? And this one is larger than 0. Okay? Larger than 0. Then that means this process is what? If that one is larger than 0, this process is, if you consider the environment, then if the delta S is larger than 0, it's the irreversible process. Okay?
Can I have an environment with negative temperature?
You can. You can.
So in that case, delta SE will be less than 0.
Yeah, that's true. You're talking about something very interesting.
Can you still like release the Q from the system to a negative temperature environment?
No,
Oh.
no, you cannot. You can only release the Q to the positive temperature. Okay, so if you, so I have no idea whether we want to go to that topic too deep, but that's the principle of laser cooling.
Negative entropy?
Laser cooling. You know, we just mentioned that laser have really high power, at very high temperature. It can melt the metal, right? But I have no idea whether you heard another technique called laser cooling. That you can, why is laser so hot, but it can cool down something? Right? Have you heard about the laser cooling? You have the trapped atoms, and then you can use the 6 laser beam to cool it down to 7 nanokelvin. Yeah, that won the Nobel Prize. Okay, for the like we call it Bose-Einstein condensate, something like that. How? Why laser is so hot and so cold? What's the reason for that? Okay, think about it. That's what you ask. Anyway, so the I hope this one. I mean, think about that. Again, if you do not consider the environment, and for a circle, we only consider this term. Okay, it's always equal to 0. Okay, it's always equal to 0. Then whether it's reversible or spontaneous depends on compare with the delta Q. But if you consider environment, if the delta Q larger than 1, it's always a spontaneous process, or it's always an irreversible process. If it equals to 0, it's a reversible process. Okay, but whether it's spontaneous or not, I don't know. There's no way to tell. Okay, because think about this process definitely not spontaneous. Okay, because of what? Because you have to compress it. Okay, you have to keep some internal work to compress it. It's not spontaneous. Any other questions? If I have no other questions, we can move on to another practice. Let's make the job more complicated, right? So this is example on the textbook. This is one example on the textbook. Have you got the textbook on syllabus? Did you got the textbook on syllabus? Probably can read this one better. No, probably do not do syllabus. That question is so long. I think we have no time to talk about cover it. We only have 10 minutes left. Let me give you a simple example. Simple practice.
Is this one still in the textbook?
No. Okay, much simpler. We have 2 cups of water. We have 2 cups of water, okay? Exactly same water, okay, H2O, H2O. One is in temperature of T1, the other is temperature of T2, okay? And then we mix them together in a larger tank. Okay, mix them together. Just put them together. Calculate the delta. Okay, this one we can call is practice 2. We have 2 tanks of water. At the beginning, one is at the temperature of 1, one at the temperature of 2. They have the equal amount. Okay, they have the equal amount. Okay, they have the equal amount. And then we mix them together. After reach the equilibrium, what's the change of the entropy of the system? Laser cooling. You know that I was working in that area for about 2 years. Laser cooling and the Bose-Einstein concept, and I quit. The reason is that kind of lab graduated in 8 years. You know what I'm saying? I need to spend that for 8 years to study. Okay, forget about it. there's another technique. It's called laser-assisted isotope separation. Have you heard about it? So I have no idea whether it's sensitive area nowadays or not. When I first came to the United States and I go to the visa office, they have a checklist whether you work in this kind of area. There's one specific area called laser-assisted isotope separation. Actually, they use the laser beam to separate different kind of isotope. And how that works? Actually, thermodynamically speaking, following the same principle. Okay, following the same principle of the laser cooling. Think about it. If we have two systems, we cool it down, we have two ways, right? One thing is to take the energy away. Then it's cooling down, right? So what if we could figure out a way to take the entropy away from the system? And then the energy spontaneously follow the decrease of the decretion of the entropy. Then the temperature also going down. So we have two ways. One is directly remove the energy, and then the entropy just follow the change of follow the energy. Or we take the entropy away, and the energy decrease, simultaneously. Both way works. Okay? Basically, laser cooling is following the second way. So we take the entropy away from the system to cool down the system. That's the principle of the laser cooling. But for laser heating, they inject the energy in. So that's it. That's the reason I told you laser is a really weird system, right? It has really high energy and really low entropy, right? That's the reason they have negative temperature. So that because of that, you can either cool down system, you can add or warm up system.
Professor, what is the significance of laser cooling?
Give you a Nobel Prize. Probably if you talk about right now, people working on quantum information, quantum computing, right? One system is a trapped ion or not trapped ion, it's a neutron atoms, right? But how do you capture the atom, right? You have to cool it down first, right? So the laser cooling is the first step for you to realize the quantum computing based on atomic system. But if you feel interested, you can just, not me, ask some other expert. I don't know whether we have somebody working on laser cooling on campus. I'm not in ground physics, but probably there is. But if you feel interested, there are a lot of people, I think in UC Boulder or Maryland, they are very engaged in this field. But anyway, so that's the soul physics side. We're working on material science. I made this statement because I don't want to get kicked out from the Department of Material Science and Engineering. Go to the Department of Physics. No, I don't want to do it. Any ideas about how to calculate the process? The first question, is this process reversible or irreversible? Everybody agree, right? Okay. So that means we cannot calculate directly. We need to find another process, right? So what's the final temperature of the mixture?
Average.
Average, right?
Average.
That's simple. Okay. We know this is an irreversible process. We do not know the details. But is there any way for us to find a reversible process that allows us to find this kind of final state? Or, in other words, we know the details. So think about it in that way. First of all, this is T1, this is T2, okay? We find a way to cool down the T1 to this state. Is that possible to do that? We just cool it down. Okay? Reversibly cool it down. Then what about the delta Q generated from this process? What does delta Q change as a function of temperature change? Nobody knows. right? The heat capacity change times the temperature change. Correct, everybody? What's the temperature change?
Same.
Hold on. That doesn't matter. I'm sorry. So I don't want to use the delta, use D, okay? Or delta. Correct, everybody? Then the entropy change is what? Now what's the entropy change of this part? No. Yeah, then the entropy change is Ds equals to what? Is that right? Is that correct? Right? No. Yeah, sorry. So this one will become from the beginning is a T. Hold on. This is the final temperature. This is the initial temperature. Correct? This is delta S. Is that correct, everybody? What about that one? The same thing, right? The delta S2, we call delta S2. Equal to CP. 1 plus T2. Right? Correct, everybody? And then, what's the total entropy change? Delta S total. Just become delta S1. Correct, everybody? Total is delta S1 plus that. So what's this equals to? Then the delta S total equals to what? Equals to Cp ln T1 T1 plus T2 plus T1 plus T2. Okay? So this one equals Cp ln T1 T2 and 4 T1 plus T2 squared. Correct, everybody? So this, and then we have 2 cups of water, and all of them, you have reach the final temperature of a half T1 T2, and then we'll just put them together, and eventually reach the same states, right? But this is a reversible process. That one is irreversible process. It's not reversible, but anyway, so we can calculate, right? So and then we can use this process to mimic that process and calculate the entropy change.
How do we know that final temperature for both tanks are the same T1 plus T2 over 2?
We just define them. So we just find the process. We just find the loop.
Equilibrium?
It's the same.
Yeah, the
It's
equilibrium.
the same amount of water in each. So
Yeah,
it's
I mean,
average.
the reason is that at the beginning we mix.
That's the only thing that I came up with.
Yeah,
so.
we mix the 2 times of water, right? We mix the 2 times of water. After we mix them, the final temperature reaches the T1, T2. T1 plus T2 divided by 2.
Yeah,
Right.
like if I have a tank of water, like of 1 cubic centimeter at like 310 Kelvin, and another one at 330 Kelvin, the mixture will be at 320 Kelvin.
They have the equal amount. They have the equal amount. They have the equal volume, equal mass.
But he's asking if they're different temperatures, how do you just average them and it becomes one temperature
Yeah.
at the end?
Yeah, how do you know the final temperature is the average?
You mix
of the
them.
two?
You mix the hot water and mix the
I
cold water,
think
mix them
the
together.
answer is it's equilibrium. Eventually
Yeah.
it'll come come to a temperature that they're both.
Or you can think about, yeah, basically that way, yeah. You can do some calculation.
The point is same.
Well, I'll tell you after the class. You don't believe it. Anyway, any questions regarding this calculation? So is this larger than 0 or lower than 0? Yeah, is this one larger than 0 or lower than 0? It's lower than 0?
Larger.
Larger, right? Because you can think about it. This one basically is what? Is half T1 plus T2 square root of T1, T2 and square, right? This average always larger than this average, right?
I just thought since you're mixing them together, it's got to be positive.
That's true. Any other questions? No. Okay. Anyway, so the let's stop here and answer your question. You have two dimensions, right? One, another. In order to reach equilibrium, for example, T1 is larger than T2, right? The heat go from this direction to this direction, right? This one release the delta Q. This one must absorb the delta Q. Correct? And then let's set the final temperature to be T. Then the T1 minus TF Cp equals to Cp times Tf minus T2.
Oh.
Right? Then you have the Tf equals to the average. Correct? But from that one, you can also
Like
see.
assuming the CP is consistent.
Yeah, but all of the water. Yeah, Cp is not function. We assume the Cp is not function times.
Yes.
And this CP is specific heat or like
It doesn't matter. It doesn't matter. But as a constant, right?
but that one doesn't take account into the water.
No.
Like cannot argue the same saying that this has like 3 moles, that only has 1 mole and
Oh, then this one doesn't work. The final temperature changes.
yeah, how like in
You
that
just
case.
add a more, right? This is no one. This is
Oh.
Gotcha. Have you decided when assignment 1's going to be assigned yet? Whatever you're going to be.
This week. Yeah.
Yeah, so I was telling you about the Bangladeshi guy,
That's fine, but cannot happen at second time, okay?
my friend.
On Thursday, so we have meeting at the PSU at the physical science building at 1. So I will show you to the postdoc, he will show you how to do it. Huh?
Is his campus physical
Yeah.
science building?
Yeah, it's that building. I will show you where it is. We have R1, right? On the left-hand side of R1 is a physical science building.